Hi, I'm Hannes,
Hello, I'm Dominic.
and today we will have a new notion of curvature on graphs that helps us understand the famous over-squashing problem. And if you want to join these reading group sessions yourself, you'll find all the information in the description.
Well, thank you very much for having us, everyone. It's very exciting to be here today to talk about our paper. Talking today is going to be me. My name's Jake Topping. I'm a PhD student at the Department of Statistics at Oxford, and Francesco, who you've just heard from at Twitter. So this paper is also by the full team, Ben, Zhao, and Michael. So big thanks to them as well. Our paper that we're going to be discussing today, Understanding Over-Squashing on Bottlenecks on Graphs by Curvature, is an investigation into over-squashing, one of the ways that the flow of information can be distorted in message passing neural networks. We're going to appeal to ideas from differential geometry to try and quantify, identify, and begin to tackle this problem. The structure of today's talk will be first I'll open and we can hone in on the problem. Then I'll hand you over to Francesco, who will take you through the looking glass and construct some powerful tools and findings. And then finally, we'll wrap up with some implementation of the method and some results. So to start with the problem, I know there's familiarity with message passing neural networks here, but just to refresh, at each layer of the network, a node's new representation is an aggregation of its previous representation and those of its neighbors. So with that, we'll dive straight into the potential problems they might face. Depending on how often you work with graph neural networks, these might be terms that you're familiar with, or they might be the subject of recurring nightmares. But we'll go through each of them in turn, just to really separate them. Underreaching is probably the most self-explanatory one. If you have a neural network with n layers, then a node is not going to receive any information from nodes that are more than n minimum distance away from it, right? Because the information is passed only along edges, it simply does not have enough layers to reach and influence the prediction on this node. Next is oversmoothing, which is the slightly more nuanced one. Graph topology is obviously usually important for learning. It was in Alan and Yohav's 2021 paper last year. I can see we've got Yuri here, where they showed that if you replace all the layers in your network with a fully connected layer, then you're going to see much worse performance, right? The result of which is graph structure isn't important. The problem is, as you increase the number of layers in your MPNN, you're going to see that the computational graph of each of your nodes starts to overlap. So if you have the green node here, it has one node itself at distance 0. It's got two nodes, the teal and the pink, at distance 1. But then once you get to a two-layer network, its computational graph is the entire graph. And this will be the case for every node as it has diameter 2. And even though they're weighted differently, you now actually have a representation as a function of the entire graph. And because of the way MPNNs and GCNs work, you can see that their representations of the nodes can become kind of more uniform or smoothed out, and it weakens this influence of graph structure and can harm performance. Then finally, to over-squashing, which is our chosen enemy for today, again discussed in Alan and Yohav's paper. The green node here at the base of this binary tree has one node at distance 0, 2 at distance 1, 4 at distance 2, 8 at distance 3. And so if the label or regression target of this node has long-range dependencies, those nodes that it needs information from at long ranges, that information is going to be exponentially compressed as it passes through these bottlenecks closer to the green node. This is present in recurrent neural nets like a seek-to-seek model, but the information compressed there is linear rather. Information compressed is determined by a node's receptive field and how that grows. Can we quantify this?
Sorry, Jake, your audio just cut off. You said, can we quantify?
Or I might have cut off. We'll never know.
Okay.
But I guess from here, I'm getting a notification saying my internet's unstable. But thank you for letting me know. If I do cut off again, just give me a shout.
Yeah.
Francesca can always take over if needed. So the Jacobian here tells us how much the ELF layer of our message passing neural network at node I, so the representation there, varies with respect to the feature X at node S, right? How much is this information at node S affecting the node representation at node I? And here we have our first result. If I and S are nodes in the graph with a minimum geodesic distance r+1 between them, and the update functions in your MPNN have derivative bounded above by alpha, and the aggregation functions have derivative bounded above by beta, which is always satisfied for some alpha and beta. For the first R layers, then you can see that the Jacobian between the node representation of I at the r+1 layer and the feature at node S is actually bounded above by the product of this constant term in alpha, beta, and R, and the like a power of the normalized augmented adjacency matrix, which is the adjacency matrix after self loops are included, and you've multiplied either side by the inverse square root of the degree matrix. So seeing this in an example, coming back to our binary tree, node S in gold is just one node in I's exponentially growing receptive field. And we see that the relevant term for this normalized adjacency matrix has this 3 to the minus R term. So it's exponentially decreasing as you start to look further into the tree. Again, calling back to Alain 21, this is demonstrated in the tree neighbors match experiment, where they show that as the tree grows, many common neural network architectures are going to start to suffer from this problem. But then the question is, if we know that the graph topology is inducing these bottlenecks, can we identify which edges in particular are responsible for the bottlenecks? And with that, I'm going to hand you over to Francesca.
Okay, so everyone again. I guess in the next section, we're going to talk about why curvature comes to play. And I think for some of you that has some familiarity with differential geometry and Riemannian geometry in particular, it would probably not come as total surprise that Ricci curvature, which is an object that has been widely adopted and studied in the category of manifolds, is important to this task because it's widely known that this tensor is associated to the information spreading in manifolds. So more concretely, you can think of picking two nearby points with some, say, parallel initial velocity, and then you want to move along this parallel initial velocity along geodesics, which are just minimal paths in the manifold. Now, what happens is that on a positively curved space, like a sphere, these geodesics will converge, so we get closer to each other. On a Euclidean space or zero curvature, they will stay parallel. And finally, on negatively curved space, like hyperbolic space, they will diverge from each other. So there are examples actually of similar behaviors for graphs if we kind of replace the notion of geodesics with that of edges. So for example, on a click, we have that for any edge, we can think of the edges departing from the endpoints of the given edge, and this will always converge to a triangle, which is similarly to what happens on a sphere. On a grid, edges departing from the endpoints will stay parallel to each other. And finally, on a tree, for example, edges will diverge, which means that the endpoints we reach will be at the distance which is greater than the edge we started from in the first place. So now any reasonable notion we want to adopt of curvature in the graph setting should capture these properties in order to behave roughly as the smooth Ricci tensor we all know and love in the manifold world. Now, the problem of actually defining a curvature on graphs is not new, but there is no unique answer, mainly because, graphs do not come with a differentiable structure, so many candidates may be studied. And usually the idea is like you want to define, the homework is like you can define one if you want to, but it has to be a map defined on the edge set that captures some meaningful property of the graph. So one is the Fermat curvature. I'm not gonna go through the details of it, but I'm not sure whether if someone has a question, please interrupt me, because I don't know if I can see the chat or not.
Yeah,
we do have a question.
Yeah,
Go on, Jason.
I can ask. I mean, there was a nice, you sort of drew the analog between what was happening on the graphs and what was happening in a sphere versus hyperbolic space. But in the sphere and the hyperbolic space, we sort of started with two parallel vectors, and I'm just trying to know what the sort of analog of the parallel vectors is on a graph. I just maybe I missed that.
Yeah, no, that's a good question. So, yeah, the problem is that for manifolds, there is such a notion that it's what you may be referring to, which is parallel transport, right? So this is why I mean by parallel velocities. Now, on graphs, there is no real such a thing. And in fact, mainly what you do is like you cannot really distinguish what are essentially, at least as far as I can tell, you cannot distinguish what are parallel and non-parallel direction, or there should be a theory for how you define that. So what you end up doing, which is essentially what both these candidates like Foreman and Alleviate do to some extent, is looking at all possible edges and measuring the convergence or divergence of edges, which at the end of the day boils down to controlling how much the neighborhoods of the I and j, which form your given edge, overlap. If they do overlap a lot, then the idea is like on average, edges departing from the endpoints will get closer to each other. That should be positive curvature. Otherwise, if they are not overlapping, that should be like a negatively curved behavior, which is what happens, for example, on a tree.
I see. Okay, nice.
While we're on questions, we've actually just had one more, Francesco. That's all right, from Yun Lu. I don't know if you'd like to ask or if you'd like me to repeat.
Yeah, please.
Then the line continues manifold graph. Right? Is that the question?
The question is there an underlying continuous manifold for graphs?
No, in general, there is not. So this is why. So I was reading a paper a couple of days ago. Now, I don't remember, unfortunately, the title of the authors, but like randomly, I know that people have tried to prove convergence results of Alleviate curvature to the actual smooth Ricci tensor under some sampling assumptions, but you have to be in a scenario where the graph is thought of being sampled from a smooth continuous space. In general, we do not have such a structure. This is why we always refer to these objects as synthetic ones, because it's like there is no, you're not assuming that there is like this has nothing to do with like the manifold assumption in typical of manifold learning settings. So these are more edge-based maps that can capture some properties that will be similar to what happens in the smooth case. But I'm gonna be more precise in a second, and you will see where I'm actually trying to go to. Can I continue or?
We've had one more, so maybe we can do this one and then we take a break for some slides and then we come back. But it's good. Please keep sending in questions. It's interesting stuff. So this is from Samar. So if we're looking at edges along latitudes, the edges will be parallel. But if we look along longitude, they will meet. So how do we define the curvature of the sphere?
The curvature of the sphere. Oh,
yeah.
So yeah, this is what I meant by, yeah, that's right. So this is what I meant by you have to, yeah, I don't want to go into details, but this is the problem I was hinting towards before with the notion of parallel transport. So ideally, the parallel transport, it's not ideally, the parallel transport depends on the path you take. So of course, the example one should have in mind in terms of convergence, for example, is of course that you are on an equator, and then you take 2 points on the equator, you look at, you basically pick one direction for the geodesics with a vector stemming orthogonally to the equator, say, and then you parallel transport it along the path, which is the equator. But there is gonna be a dependence on the path. As I said, these questions are relevant because on a graph, in principle, I have thought about that. I don't have a definitive answer yet, but in principle, you want to have a similar sort of pattern where you don't look simply at all edges, but there's going to be some dependence on the path, and some of these ideas have also been explored to a paper. I cannot discuss much into it because it's not out there yet, but it's a submission to the last conference, I think. But these are all good questions. It's true that you should have a dependence on the path. But yeah. Okay. So what I was saying, getting back to it, is that there are already candidates for discrete curvature on graphs. These are all edge-based maps. One is Foreman. I will not give you the details of the definition, but this is just a very fast, very efficient map. It's combinatorial, but it has limited power in the sense that even its augmented versions, they can only distinguish triangles. So they, for example, on the grid will not be flat, but will have negative curvature because this quantity will not distinguish 4 cycles, for example. On the other hand, Olivier curvature is much more powerful. So this is related to Waterston distance optimal control. And I think in computer science communities, this is called something like Earth mover or distance or something like that. But it's very powerful. So there's a lot of theory that seems to point to the direction that Olivier curvature is, at least now, for the time being, the best candidate we have. But it is harder to control. Analytically, most importantly, it is expensive to compute unless we resort to some approximations. So can we find ideally a balance between the two of them that can retain some computational tractability, but being more powerful in terms of expressivity than Foreman? But note, this a disclaimer I have to make, that all the stuff I'm saying and the relation between curvature and quotient can basically work with any curvature definition, provided that this curvature definition captures some properties related to volume growth and dispersion of edges, as you're going to see in a minute. Right. I'm trying to see now why. Yeah, I think there's some lag with the slides. Right. So I think I can control it better now. Okay, sorry about that. So I'm going to do some notations. These are not crucial, but what we care about is number of triangles at a given edge. This is just the intersection between the neighborhoods of I and J. Then the number of force cycles based at a given edge without counting diagonals inside, because we don't want to overcompensate for triangles. And then there is this nasty guy, which is a bit technical, and the reason why it comes basically out of it is just because it allows us to derive a nice comparison with Olivier curvature. But essentially what this object is measuring is the degeneracy of force cycles. In other words, how many force cycles we have that are based at the edge I and J, but traverse a common node. Like for example, here, if you look at this graph and we care about the edge 0, 1, this degeneracy factor would be 2 because we have 2 force cycles passing through node 5 based end as 0, 1. So this is the definition of what we have termed balance formant. So what I want to sort of point out are a couple of things. So first, this is a normalized quantity because we are normalizing by the degrees. So for example, it will never be more negative than -2. We see that triangles account positively for the curvature, and similarly for cycles up to this degeneracy factor. But now, I don't want to bother you with the details. In fact, it's going to be hopefully clearer in a second in the next slide why exactly this formulation. But let me, for example, mention that we recover all the patterns of like the behaviors that I was mentioning before. So for example, on a cycle, which is the kind of graph counterpart of S1 or of the circle, the Ricci curvature is going to be 0. On a grid, differently from formant, we can recover at 0 curvature, so this is flat behavior. On a click, we have positive curvature, and finally on a tree, we have negative curvature. But what is also important actually is like that in all of these cases, this Ricci curvature, this balanced Thurman curvature coincides with the Olivier curvature. So this is not surprising because essentially the reason why you've seen this formulation is because essentially this balanced formant truly is an expansion or an approximation of the Olivier curvature, right? So we have this theorem that says essentially that we have a lower bound for Olivier curvature given by balanced formant curvature. And so what are the things I want to stress here? So first of all, the way you should think of that is like up to 4 cycles, this balanced formant is an expansion of the Wasserstein-based Olivier curvature. And yeah, okay, this is probably not the place, but like it's sort of a generalization up to 4 cycles of results of Just and Liu. But the consequences now are important for us because there is a rich theory for Olivier curvature that now we can immediately borrow and adapt to the balanced formant case. So for example, we know by result of Peng that now if our balanced formant curvature is greater or equal than k everywhere in the graph, then there will be a polynomial p such that the size of the R-hop neighborhood of each node is going to be bounded by this polynomial. Now, if you remember what Jake was mentioning a couple of minutes ago, we know that exponential volume growth is associated with oversquashing. So in other words, when you have exponentially many nodes in your R-hop neighborhood, you're going to have compression of information inside an MPNN. And now this theorem is actually telling us that if the curvature is positive everywhere, then there's not going to be oversquashing because the number of nodes in your R-hop neighborhoods is at most polynomial, which kind of leads to the following question, which is, can we actually identify the edges that are responsible for the oversquashing as those that have large negative curvature? I see there is a question, I think.
Yeah.
There is. So first there's one from Hans, which
Yeah.
I suspect has something to do with the graffiti.
Yeah.
Yeah, what's happening?
Yeah, you're saying, I'm sorry about the confusing drawings here, but you're saying the now negatively curved edges correspond to oversquashing. And if we have no, if we have a curvature greater than 0, then we have no oversquashing happening. But if in the graph that I drew down here, isn't the curvature for every edge 0? Like if this goes on infinitely, so to say, like the number of these, this is like a star graph with infinitely many branches, or let's say 1,000,000. And
so there is like an important point. You have to be not simply possible, but there has to be a lower bound. Okay, your curvature, your example does not satisfy that, because you are requiring to get this polynomial behavior. You're requiring, I don't remember exactly the asymptotics of Peng's paper, but you have to be larger or equal than some, however small, positive number along each edge to get the polynomial volume growth.
So what would the curvature be here? Like, am I right that the curvature for these edges would be would be positive?
It would be once you got slightly further out, but for the 3 edges around your center there, they would be negatively curved.
Oh, okay, then I got that wrong.
Because if there's kind of the center node has degree 3, and then 1 out has degree 2, so you got 2 over 3 plus 2 over 2.
Can you
That's
maybe
1 2/3, and then
like,
-2 is minus.
No, I think I mean you may be right. I mean, if the graph you're talking about is the red one you've drawn, right?
Yeah, can you maybe go back to the formula so everyone has?
So yeah. So you're interested in the central node, am I correct?
Yeah.
So
Yeah,
central to
so-
1 out, yeah. So if you got DI is 3, DJ is 2, and then everything beyond the -2 is 0 because there's no triangles or 4 cycles.
Yeah. That's right. It is negative.
Yeah, it's gonna be
that's right.
negative.
Yeah.
Yes,
Well, okay,
that's right.
but if we now had like let's say DI, so I is the central node, and then we're not saying we have 4, we have maybe 1,000 there, and then this is almost 0. So the 2 over DI is almost 0, and then we have +2, -2, +0, right?
It wouldn't be +2 though, because the DJ is going to be 2 because it's connected to the central
+1.
node
Yeah.
and the one further out.
Yeah.
So you're going to approach -1.
Good. And it is going to be -1, the curvature.
But I mean this is not. Yeah, okay. This graph now has negative, but the point is more about you can get a click, and you can get a click that is positive it has positive curvature everywhere, and then if the click is huge, you're gonna have a huge number of nodes in your one hop neighborhood. The point of this theorem is you should look at them as what would be the expansion. So this is like what would be the volume growth in terms of the radius. So this is what you should care about. But yeah, in the case in particular you drawn do not satisfy it because they don't have positive curvature.
Okay, thanks. But we have another question in the chat.
Yes.
Does this K, the K we use to bound the Ricci curvature below with, do anything? So, for instance, is the polynomial degree a function of it?
I think so. As I was saying, I don't remember exactly the asymptotics of the paper, but definitely this is going to be, I assume that the smaller the K, the larger the exponential is going to be. The larger the polynomial is going to be, but I don't remember the asymptotic expansion. But of course, yeah, there's going to be a dependence on K. But once again, drawing graphs that have positive curvature everywhere, it's going to be hard, exactly as for the smooth case. So the gist of this theorem is more about the curvature is possibly the right object to monitor what is the volume growth or what is the number of nodes in the hard-hop neighborhood. Because, for example, in the limit case, where the Ricci curvature is positive everywhere, then for sure, there's not going to be exponential volume growth. So in other words, this is an object that is probably capturing what we are interested in terms of squashing. But the main theorem of the paper that I'm going to mention in a second is actually addressing this question more, I guess, more precisely. Right. So I'm going to introduce this convention, but actually be quick so that then we have time also for the results. So I'm just going to say that the Ricci is very negative if, remember that the definition is such that you, yeah, I've now realized I forgot to write what the condition was. Essentially, there exists delta such that Ricci of ij is smaller than -2 plus delta. So remember that -2 was the ideal lower bound of the curvature because of the normalization. We are asking essentially to be close to this bound by delta. And the condition of delta is just saying we want to avoid pathological cases where the edge is very negatively curved because there exist many force cycles that are degenerate in the sense that pass through the same node. So the informal statement is the following. So if you have a very negatively curved edge, then you will have many nodes that are at hop distance 2 from node I, such that your NPNN will essentially struggle to send messages from I to such nodes in 2 layers. So despite being at our hop distance 2, these 2 layers will not be enough and will fail to send messages. And this is just a more explicit version of this theorem where essentially what we are bounding, how we essentially we are measuring the failure of the MPNN is again via the Jacobian by showing that on average, these Jacobian are going to be small, order delta to the 1/4, and this is going to be true for a large number, delta to -1 nodes. So the message then is the following. So we knew that the topology, the graph topology enters the MPNN and affects how messages are propagated via the Jacobian. We've measured that. But now what we've done is get into a more local and refined expansion of the right-hand side by actually showing which edges are responsible for the oversquashing. And of course, the benefit of this analysis is that we can now identify bottlenecks and by studying the curvature. And I'm going to finish this section by mentioning a few things about bottleneck that are going to be relevant for what Jake is going to say next. So there is a notion that some of you may be familiar with that's been widely studied in the graph community world, that is that of Chiker constant. So suppose that the setting where you have a graph that has 2 communities that are separated by few edges. So communities here, I'm referring to the topological notion community, nothing to do with label distribution here. So we have a bottleneck because we have few intra-edges, many intra-edges. The information from propagating to one community to the other has to be squeezed through these bridges. And this property is captured by the Chiker constant, that is the isoperimetric ratio. So in other words, that is measuring, this Chiker constant is a number that is measuring how easy you can disconnect the graph into 2 communities. And I'm not going to dig deeper into that for the time being. But what is crucial, in fact, is that there is a nice result that basically extends what is known for the manifolds case, that is the Chiker inequality, that relates the Chiker constant to lambda1, which is the spectral gap. In other words, it's the smallest positive eigenvalue of the symmetric normalized Laplacian. So in other words, the smaller the Chiker constant, or if you like, the spectral gap, the easier would be to disconnect the graph into 2 communities. So in other words, the Chiker constant is kind of measuring in a rough way how bottlenecked the graph is. And I'm saying rough because it's just a number. So it's a global measure, it's not local. And it only sees the partition of the graph into 2 communities. But since we've seen that negatively curved edges induce bottlenecks and therefore cause oversquashing, one would expect a relation between the curvature and Chiker constant. So in other words, with a spectral gap. So the answer is affirmative. This is just by relying on our comparison theorem and the result of Lin et al. But this correlate, essentially, the way you should think of that is the following. In principle, if you modify the graph topology by removing edges that are negatively curved, you may see an improvement in the Chiker constant. In other words, you may, at least in principle, improve the bottleneckness of the graph. And you are going to see that this is something that is not, for example, possible with diffusion-based rewiring methods. So I'm going to stop here, and I'm going to leave to Jake the final section of this talk.
Sweet. Thank you very much. So we've got kind of a nice war chest of theory now to come and try and tackle this oversquashing problem. And I guess one of the more simplistic approaches to try and improve the performance of a message passing neural network is to apply some rewiring as pre-processing, right? If your graph structure isn't amenable to the graph learning, then change it and use the resulting graph topology as the input to the neural network instead. So we can see here that instead of taking this dumbbell-shaped graph with a very small bridge in between it that has a very negatively curved edge at the center in blue, we can try and support this edge a little bit more and alleviate the flow between the two cliques. We would like to take a process on the graph to normalize the curvature. All right, so if we look at the manifold example to start with, we have quite a pinch in the middle of our manifold with the red signifying positive curvature and the blue signifying negative. And we want to run some curvature flow to expand upon the negatively curved section and contract upon the positively curved section in the hope of smoothing out and normalizing this object, right? Removing the pinch. And with our new, go on, Hans.
Yeah, why do we want to do something to the positively curved sections? Like, yeah, you were saying we want to normalize the negatively curved sections, and we want to also do something to the positively curved sections, and you also remove positive edges in the end, right? But why do you do that?
That is something that we'll look at.
Okay.
Well, not to negate the question, it's a great question. I guess in a rewiring such as this, it's not necessarily that removing edges is going to help over squashing, right? Positively curved edges have been shown in Francesco's section to improve over squashing, right? If you have kind of a fleek like you see on either side of this bridge, you see that there's going to be like limited polynomial growth in the receptive field, so you're not going to see such over squashing. You could kind of postulate as to whether having a too densely connected graph would be unhelpful for graph learning, but that's not something we have results on here. The main kind of impetus for taking this normalization is exactly that, for normalization, right? If you say add edges in useful places and remove edges where they're not useful, then you can try and preserve, say, an average degree on the graph in the same way as in a Ricci flow or a normalized Ricci flow. You might try and preserve the volume of the manifold.
Okay, so
and kind of try and limit the impact on the topology.
You basically prefer to be inspired by the Ricci flow and preserve something like the volume instead of preserving the original connectivity and having a lower graph edit distance in the end.
Yeah, I guess this is where you can take different metrics on what makes graphs different, right? So if you just look at graph edit distance, then yes, removing edges is going to increase the graph edit distance. But you might inflate the average degree or something like that, or the degree distribution. So, obviously you can try both, and it's a parameter we can fit later. We're going, Francesco.
Yeah, no, I was saying that maybe something that we never mentioned explicitly in this talk, but it might be a partial answer to your question, is that then, if you apply these tools to a knot classification problem, now there is all this business of how to deal with different levels of homophily, right? Now, it's not surprising that these methods, in terms of rewiring, that the ones that Jake's going to show, would offer better performances on heterophilic data sets. So what you would expect, of course, empirically, you can say, oh, let me tune the hyperparameter, how much I want to add edges to support bottlenecks, how much I want to remove edges. But the intuition, I think, for your question is that on an heterophilic setting, whenever you have a very positive curvature, it means that basically there is a region which is very dense, and information is going to propagate very fast in a heat diffusion type of way. So, and now if you're in a heterophilic scenario, and you assume therefore that you have very low heterophily, which means that most of your neighbors, most of the nodes you are connected, are not sharing the same label, removing edges that are in very dense regions may be helpful. Of course, if you're looking at a very homophilic graph, then that's probably adding noise, but this is like, again, it's a bit intimately obeyed, not entirely manifestly related to the morphology of the graph, and you should, I think, more think about heterophilic setting, because this is where the whole problem of long-range dependencies makes sense. If you only care about your neighbors, there are no long-range dependencies. The diffusion heat equation works fine. But yeah,
yeah, nice. Those are very cool intuitions. Then Surya, do you want to ask a question?
It might be slightly naive, but I guess the explanation that was just given by Giovanni, I was just wondering whether that connects the curvature information to the size of the click some way. I mean, when you say that some part is very densely connected, I was just wondering whether it has something to relate between the curvature information and the size of the click.
Yeah, it does. It does. I mean, you have, in general, a densely connected part of the graph, for example, can be kind of described as a region of the graph with very high mean clustering coefficient. So any pair of edges would generally be closed in a triangle, and these dense regions would tend to have positive curvature. So this, and in the ideal case, the curvature is maximized on a click where everything is closed. So you can capture these dense regions using curvature information.
Right, and what repercussion would that have on the Ricci flow in this case?
What intent? You mean the repercussion as in
the impact? Yeah.
As in removing edges, you mean?
Yes.
So I think maybe Jake is gonna address that in a second, but it's probably important that for people that have heard of Ricci flow, you should think of that as backwards Ricci flow. So this is not just, so Ricci flow is like, does not modify the manifold. It modifies the metric. What we are doing is more akin to surgery. So you use the information of the curvature to decide where to remove the underlying space by surgery operations. So there is a kind of, somehow, as Jake was saying, this is sort of normalization of Ricci flow, but that you can account for that in some way. But I guess a more heuristic, intuitive perspective should be in a non-classification task to think about roughly what is the morphology of the underlying graph.
Thanks a lot. I think I had a lot of other questions. I'll take it offline. I guess it will be okay to email you guys. Thanks a lot.
Okay.
Have to chat more. And we had Jason next.
Sure. Yeah, I guess maybe this is just naive, but like there's something that's kind of strange about rewiring to me. Like you're changing. There's a lot of like information in the topology of the graph, and you're kind of changing the topology of the graph in order to address the fact that there are these bottlenecks, and the bottlenecks make a lot of sense. But it feels like in doing so, you're destroying information. And do we have some notion of I'm now suddenly connected to a neighbor that I wasn't connected to before. I can suddenly talk to someone in Europe when I couldn't talk to them before, even though I don't have an direct connection, and that feels surprising. I mean, do we have a way of kind of, this is looking at the graph as a black box and sort of saying, I'm just going to rewire things in such a way that it's nicer from a message passing point of view. But at the same time, I'm losing information about the underlying topology of the graph. And I mean, how do you deal with that sort of trade-off? Does that even make sense as a question? I don't know.
Yeah, no, it totally makes sense as a question. And kind of the impact that you're having on the graph is something that you can definitely pay attention to. You should pay attention to, right? There's kind of, I don't know if there's too many results, like firm theoretical results back and forth on whether you actually need the input graph. Obviously, it improves performance, as we mentioned earlier with the experiment in Alain's paper. Removing that can hinder performance, and the plus fully connected method that they explored in that paper started with the original graph, and then in the final layer of the network replaced that with a fully connected layer. Right, so you get the initial graph structure, and then you kind of alleviate the bottlenecks right at the end, just to allow these nodes to talk. We will look at, and once we've discussed the method a little bit, like how much do these methods alter the graph, and is it something we should control? So I guess it's something we'll cycle back to in a little bit, but yes, I do agree. It's something worth paying attention to.
And then I guess a related question is I mean, the other kind of axis of variation that we can play with when we're doing learning on graphs is obviously like the width of the channel that we're supplying. You know, how large is the vector of messages that we're passing? That has computational inputs, but you can imagine sort of blowing up, you know, that. And it seems like that's sort of another way of dealing with bottlenecks in some sense. You know, if you have a way of sending, if we're not sort of constraining what information has to be sent across this bottleneck, you know, to use your Dumble example, if I double the number of the depth of the sort of the width, being imprecise, but double how long my sort of vector that I'm sending over the edges. That's also going to alleviate some of that bottleneck, because I can now use that larger vector to put more information in and send across that. I don't know. That feels like a way of doing this without throwing away the information of the topology. But maybe that's just an empirical question as to how they address these. I just don't have a way of thinking about like how do we trade off these two ways of addressing bottlenecks, and if that even makes sense.
Yeah, totally.
If I can ask a question, Jason, when you think about graph topology, what kind of task do you have in mind? Like, do you have in mind graph classification, for example, or do you have node classification? I have an answer for both. I'm trying to understand what do you have in mind, though.
I mean, both. Yeah, I've kind of worked on problems in both, and actually, I don't do a lot of work in graph, particularly in either of those problems. But I think about sort of permutation equivariance in general. So
yeah. So I guess like okay. Let's start for node classification, for example. So node classification, at the end of the day, you really don't care about the graph topology, provided that, in fact, most of the algorithms that work, and I'm not saying fancy versions that store, I mean, it's true that you can augment with and so on. I'm not a fan of doing that in general. I'm not a fan of augmenting stuff, and because most of the times this is like hoping that it's going to work because you have more room. But like, but in terms of node classification, the GCN works because you lose information. For example, you increase the entropy, you do diffusion, and that allows you to classify. So at the end of the day, for node classification task, it's a hard question, and I think an interesting one, understanding how the topology and to what extent the topology matters, and in terms of what is the difference between computational graph. But in terms of graph classification, for example, say you have two graphs, and by rewiring with one step, I can get to, say, the complete graph in one case. In the second case, I cannot. Then these two graphs are not isomorphic. So you can see that the rewiring has given you information about the isomorphism distinction between these two graphs. So it's very common in geometry to massage shapes you're not that happy with to make it work. But you should think of that as also giving you a lot of expressive power that can be exploited even in graph classification. So even if counterintuitively, perhaps you can modify the topology, but that can give you more information about what you had initially, perhaps comparing with some other graph. Now, this is more applied for like graphs that are perhaps like, I don't know how to call them, like academic graphs. For molecules, maybe that's different. And we have to see what happens when now the graph is a physical one. Then I agree. In that case, you should be careful in how to modify the topology, but because then the graph is a real entity. It's not a similarity graph or a citation graph. It's a true physical one. So altering topology may be harmful if not done cleverly. Then in that case, it's a different business.
Yeah, okay, maybe that's actually the kind of key thing is like the kinds of problems I've thought about. It seems to be a mapping to something that's very real. Like I've worked on this in context of stats, which is obviously not a graph necessarily, but there you're literally changing a logical formula when you're when you're adding or removing an edge, and you know, there's something kind of weird about that. But maybe let's take this offline. Good.
Just to wrap up that the kind of alternative that you proposed about, say, doubling the width of your layer as well. There will be architectures that let you kind of solve problems with that. But the problem with, say, using a GCN is that you don't get to control whether the information from node I goes into entries 1 to 10 and node J goes into 11 to 20, right? They're both going to go into both because they share a weight matrix. So you don't actually get around it like that. Once you've reached a width that can express the information for one node, like you don't really get improvements after that in theory.
I mean, I get that in the context of GCNs. I'm not sure if that's a problem with the GCN or a problem with the general approach. Like, if you just think
possibly both.
Information theoretically, like if I've got a limited channel, is kind of the problem that we've got. And sure, you know, with the GCN, that you've got all sorts of problems. But if we're trying to overcome a limited channel, one way is I can make more channels, or another way is I can just increase the width of the channel. And you know, we do have that second option, and it would be interesting to try and think about ways of kind of comparing between the two approaches.
Yeah.
Admittedly,
like to
you're right about the GCN. I'm not sort of I've taken too much time.
I would like to add that I am very much on Jason's side, and he basically said most of the things I wanted to say. Like when I raised my hand, one thing that happens is, like, suppose that these are indeed two communities, that you have city A and city B, and there's a bottleneck here because there's road between the two is too narrow, but you want information to pass. There's two strategies. The one that you employed is building many roads across different main streets, or the other strategy, which is what is employed usually, is to make a big and fat highway here that allows more information to pass. And now Jason's proposition about making the width larger is a good proposition, but it's difficult to work with in standard graph neural network because you have different nodes and different edges that have different hidden dimension. So the proposition that I would like to do is instead regularizing the nodes based on the Ricci curvature, such that the lower the curvature, the less the node is a bottleneck. And the more you regularize it, such that the message it contains is sparse. And that would mean that nodes that have like very low connectivity, that are not a bottleneck, would only have like information in some part of the vector matrix. And nodes that are a big bottleneck would be less sparse and have like information all over the vector. And this means that there can be more information that passes through these highways. So in that way, you regularize the kind of the streets, such that if you have a street that is important in connecting different communities, you are able to pass more aggregation, more information, because the rest of the information is sparse, and you are able to map it onto a same size vector with minimal loss. And I think this would help, like, in some sense, make a direct use of the Ricci curvature. So having a regularization that is directly proportional to that curvature, instead of like trying to find where to build a new street, and going into like the problem of maybe destroying the topology of the graph when doing so.
Yeah, no, I totally agree. There are definitely more involved methods you can take, which involve varying the architecture or the regularization. There was a paper last year called Curvature graph neural networks, which I don't know if it incorporated in exactly this way, but it did kind of weight the connections by some Ricci curvature. I believe they used alleviate. Yeah, the kind of adding and removing edges came from a restraint, I guess, that we wanted to create a pre-processing method that didn't need to alter the architecture and works just on combinatorial graphs, so with no edge weights. And that's why I guess we have this initial kind of coffee shop napkin solution. But yeah, that's a super interesting idea.
I think you should check. I was about to say, but the author of the paper actually wrote it. Increasing the size and in general, this width, increasing the width of the bridge. If it's exponentially growing the receptive field, it's not that easy. Like you're gonna pay a lot in terms of width cost. So it's a trade-off. Either you modify the graph in some way, or you're gonna pay a price in terms of width. And I think it's just I'm reading the chat, but they had a nice combinatorial argument in their paper as well for I think a 3, if I remember correctly. Yeah, it's an interesting approach. It's a trade-off, but Uri answers is also to the point, I think.
Well, I guess we'll just smash through the questions in chat quickly, if that's all right, and then come to you, Alexander. Just because I think we can wrap them up quickly. So Benny's question was, what does the curvature formalism really give us? Why don't we just look at the Cheeger constant and the bottleneck edges? We can find these algorithmically. And Hans is right. Calculating the Cheeger constant is incredibly expensive. You'd have to go through and calculate all of the possible cuts that you can get. You can approximate it, but it's still not a super great bound. Whereas calculating the curvature on the graph, we've written a CUDA kernel to do this, and it's quite efficient. And as Francesco's shown, gives you some good indicator as to the bottleneckness of edges. Do we indicate that these are fake edges? Ben's right. No, we don't. But again, that's an interesting idea. We've been looking at simple graphs, but looking at the different edge types is something that we tried in a couple of experiments and would definitely be interesting. Isn't there a danger of increasing the oversmoothing problem when adding edges? Yes, in theory. If you add edges to the point that all nodes kind of end up sharing the same computational graph with a fewer amount of layers, in theory, yes, that's possible. Yeah. I feel like Etienne said, I feel like that adding fake edges would be more problematic for link prediction tasks. And as Ben said, yes, we think you're right. As was mentioned in the Deagle paper, we also haven't used this method on link prediction tasks. I guess that's a different category of problem. And we can come back to the rest. But Alexander, please do go ahead.
Yeah, thank you, Jake. Francesca, I wanted to go back to what you said about the physical graphs versus academic graphs, right? So you said that you'd be much more careful in adding new edges or modifying the topology when it comes to a physical graph. And I was wondering, like, what's your intuition behind it? Is it because when we talk about those academic graphs, they usually are talking about something which is maybe not necessarily physical, and in this sense, it's a more noisy representation, in a sense that we could maybe think of it as nodes being, a representation of some latent variables that we don't take into account when we're working on the graph, or is there something else?
So I guess my intuition was, and maybe wrong, but like, for example, when you think about molecules, like the existence of higher order structures there can be associated to physical properties. And therefore, by modifying that, especially like as a pre-processing done differently, that could be a different ballgame. But as a pre-processing, that could be harmful because you're gonna, for example, you can compromise ring structures, so you can compromise higher order structures that are actually key elements, perhaps in monitoring some, I don't know, electric or energetic quantity you want to predict. On the other hand, a cycle structure in a citation network or whatever, it's you can mess up at the end of the day, especially if you're interested in node classification. The computational graph is much more important. At least that's what I would say compared to higher order structures, for example. And in fact, it's not surprising, I think, that in Allen and Yahav paper, they propose to add a fully connected layer for QM9, but that's done at the end. So that's done in other words, when the information from the topology in terms of higher order structure and so on somehow has been captured as best as the GCN model could. So that's, I think, what I had roughly in mind when I made the distinction between physical and non-physical graphs. But yeah, this is just I think an intuition, nothing more.
Yeah, no, that's very interesting. I mean, I think it's similar for social networks, right? We could think of them rather as maybe dynamical complex systems than something that, you know, when you change one element, some higher order structures that just disappears or maybe changes its attributes significantly. So yeah, so that's I think that's a very interesting observation, I think, and you know, and I feel like it has some practical implications, right? When you work, to what extent you can safely modify the topology of your graph depends on what type of graph it is and what kind of information it conveys, what kind of system it is, right?
Yeah, I think that's to some extent the true question of this paper in disguise. Yeah, I think that's it. We don't provide a definitive answer, but at least it's yet some an investigation in an area that is not that, you know, people are worried when you modify the topology of the graph. I did a PhD about modified structures, so I'm not that worried in general. But like, it's true. It's the question you asked. It's kind of what motivated us in the first place, I would say.
Great, thank you.
All right, sweet. Let's we've talked so much about the method. Let's go through it. So the method that we propose as kind of this initial curvature-based rewiring is stochastic discrete Ricci flow. I don't actually know how to get rid of Dominique's beautiful drawing, as helpful though it was on the previous slide. Do you know, Dominique?
They're gone now. Yeah.
Clear, they're gone. Thank you so much.
Sorry, I forgot to remove them.
That is completely fine. It was very helpful on the previous slide. So yeah, as we've said, the kind of very high level is add a good edge and remove a bad edge. So bad is obviously very subjective. If you want to preserve all of the edges that are in your graph, then there are no bad edges. Right? But what's good and what's potentially bad, we're going to decide with curvature. So the algorithm, as stated in the paper, is here. Your input is your graph. You have some temperature tau, because this is a stochastic process. You have a max number of iterations that you're going to run for, and you have an optional upper bound C+ for a Ricci curvature. Step 1 is the add edge step that we had in green. First, you find the edge ij with minimum Ricci curvature, and then you find a family of candidate edges to add, which are the edges between some node k in the ball of radius 1 around I, and L, which is in the ball of radius 1 around J. What does this mean? It means that the surgery, the addition of the edge, is necessarily local, right? The new edge has to form at most a 3 or 4 cycle with this edge ij with minimum curvature, because 3 and 4 cycles are what's going to get picked up in the balance form and curvature that we are using. Once you've calculated the potential improvements from all of these candidate edges that you could add, you sample an edge to add with a softmax probability of this improvements vector times tau. And this is where tau affects the stochasticity. If tau is infinity, you're always going to pick the edge that gave you the strictly best curvature improvement. As you lower tau, it gets more random. And then once you've sampled this edge, you add it to the graph. Step 2 is removing an edge. This step is simpler. You just take the edge with maximum Ricci curvature in the graph, and if that is above your upper bound, then you remove it. Again, if you have, say, a physical network or other network where you want to limit removals or do no removals, you can set C+ to be high or to be infinity if you would like to remove 0 edges. You do this until convergence, where you can't do both of step 1 and 2 in a row. or the max number of iterations has been reached. The max number of iterations, putting a upper bound on the graph edit distance between the graph and the preprocessed graph. To kind of go through an example of this, we have a simplified version of the dumbbell graph just to see it in action. So first, we'd find the edge that has minimum Ricci curvature. It's this bottleneck edge in the middle. And we look at the candidate edges that we could add to improve the curvature of this and try and alleviate the bottleneckness. Once we've calculated the improvement, we can sample a new edge to add that's formed a 3-cycle with this bottleneck edge, and in theory, improved the flow of information between the two cliques. Then you move to the removal step, identifying the edge that has highest curvature, which say is above this upper bound, and you remove it. Then you go back to adding an edge. Say this new edge that you added has the next most negative curvature. You sample a new edge. You can see the bottleneck start to thicken out. And then suppose that as you come to the removal step, it has maximum curvature, but your upper bound that you've set is high enough that this edge actually isn't removed. We don't remove it. Then to suppose we've come to convergence, take this edge and suppose it has minimum curvature, but that there are no candidate edges that you can add that will improve the curvature of this bottleneck, or non-bottleneck in this case. And once those two have happened in a row, we're converged and are done. So this is our initial curvature-based rewiring method. But when you talk about graph rewriting, you also think about graph diffusion convolution, I'm sure, or affectionately known as Deagle. So Deagle is a method from Curvature et al. 2019 from Stephen Gilman and the team, and it rewires the graph by graph diffusion, as Francesco mentioned earlier, and it leads to significant performance on a range of tasks. Right? Are we here to suggest that we've come up with a new family of rewiring methods to knock Deagle off of its diffusion-based podium? No, Deagle is great. Both methods will have their pros and cons, and so we're just trying to add another family of tools to your toolbox. Deagle is very good on kind of homophilic data sets. Where is it potentially not so good? The first one is, as Francesco mentioned earlier, is that GDC or Deagle is based on an assumption of homophily, which is common but not guaranteed. This is mentioned in the paper by the authors. Homophily being birds of a feather flocking together, and they say that this method might not work so well on heterophilic graphs, which, as Francesco said earlier, curvature-based rewiring methods may do. And then to relate back to the spectral properties section that Francesco mentioned earlier, if we look at GDC or Deagle with the personalized PageRank kernel, so this kernel R alpha, this is used to measure the diffusion between nodes. Please read the paper for the details, or the Deagle paper. But you can see that we actually obtain a constraint on the Cheeger constant of the rewired graph. So the important part of this theorem is this term in the top right, this Cheeger constant S, alpha, which is the Cheeger constant after a Deagle rewiring with this diffusion parameter alpha, is bounded above by a multiple of the original Cheeger constant. What this means is that if you have a poor Cheeger constant before, if you have kind of a high alpha, then you're going to be limited in the improvement that you can make to the Cheeger constant. And to alleviate this bound, you will need to take quite a low alpha and blow this term on the right up, which results in a lot denser graph. So TLDR of that is try both. They're suited for different graphs. You can make a decent prediction on which one might work better, but also it's, why wouldn't you try all of the methods available to you? So I can see a question from Hans.
Yeah, why does the diffuse, or why does Deagle even help at all for alleviating bottlenecks, or why should we expect it to?
Why should we expect it to help alleviating bottlenecks?
Yeah.
I guess if you can take hyperparameters into Deagle such that it will add quite a lot of edges to your graph. And If you add enough edges, then
Okay,
you won't have these bottlenecks.
Compared to adding random edges, I mean, if you add more edges at some point, yeah, you will alleviate bottlenecks. But why are they better?
Well, yeah, and I guess this is the discussion we mentioned earlier, right? Is preserving the original graph structure important? So I remember in the paper, in the Deagle paper, they showed that they could approximately preserve average degree while improving performance, but that they did still see further improved performance by increasing the average degree, some cases by quite a lot. And that's something that we'll see in our results section too.
Yeah, but I just mean the Deagle rewiring has nothing to do with bottlenecks, right? Or I don't see why it should alleviate bottlenecks more than random edges.
I don't know if it does. I'm
Francesco.
sure Deagle is more sophisticated than that, but yes, it's not something that relates directly to the curvature. It's not something that relates directly to the bottleneckness. Right? Francesco, I can see you unmuted.
If you're saying that Deagle is more sophisticated than that, then it sounds like their aim is to alleviate bottlenecks, right? Or like this definition of bottlenecks. But like if you're just looking at homophily and getting things that are close in random walk distance to be closer in our computational process, then that's the advantage that we get from Deagle, and maybe not related to bottlenecks. But Francesco?
Yeah, I'm sorry. I'm not sure I'm getting your question, mainly because after an hour, my concentration span goes to 0. So are you asking that you should not expect Deagle to alleviate the bottleneck? Is that your question?
Yeah.
Yeah, and I guess that makes sense. If I can take this one quickly, if that's all right, Francesco.
Yeah.
We're not saying that this is a failing of Deagle. It's very much not. Deagle is a great method. But if you have a graph that is suffering from oversquashing, that is suffering from bottlenecks, then maybe a curvature-based rewiring method will help that. You know, maybe you could even try both. That's something. It's a revolutionary idea that we haven't tried, running both in succession, but it could work. Right? It's just again, different graphs, potentially different tools will help.
Yeah, I'm not saying that this is like some competition or whatever. I was just wondering if there's an intuition that I'm missing on why Deagle should help against bottlenecks.
In general, you would not expect that, right? Yeah. And in fact, this term is proving that. The question is, how would you show formally that Deagle is probably not suited to address problems with long-range dependencies?
Oh, I don't see the connection.
Yeah, exactly. But how you would check that? How would you prove that, like in a formal way? Because you can have an intuition say, I don't see why Deagle generally would help alleviating the bottleneck, which is the truth. And in fact, this is what this theorem is kind of saying. But how would you? What this slide is saying essentially is that you should not expect Deagle in general to alleviate bottlenecks. In fact, it's a method that is very effective on high homophily. In fact, we show this using the Chiger constant, that you should not expect this alleviation to happen by using Deagle. So that's the, you see the point more now? Otherwise, I don't see your question. The point of your question.
No. I was just like, in your paper, you were like, yeah, we're showing that I left with the impression, yeah, we're showing that Deagle doesn't actually help against bottlenecks. And then I was thinking like, oh, why, what am I missing here? Why should it help against bottlenecks? But yeah, I mean,
I think, we're not, I think we're not criticizing. So yeah, I guess that's, Jake was pointing this out like earlier. We were not saying that they claimed something that was not true. It was more about trying to understand better, like what the algorithm was doing.
No worries. I just thought I was missing something, but I think
no, you were not. You were not. Good. I think your intuition is correct. Yeah, it's definitely correct, of course.
Yeah, but another thing that I was wondering is, like, we Like we're trying to somewhat preserve the graph structure. If you're, or will you show these experiments with the
Yes.
how the node degree stays the same? Yeah, then let's get into that later. Good, thanks.
Cool. All right, sweet. And now I believe we're coming to results. So the experiments that we ran were semi-supervised node classification with a simple GCN using the given rewiring for a pre-processing. Right, so semi-supervised because you're using the graph structure across the train, validation, and test sets. The plus FA method is the last layer fully connected method from Alon and Yahab 2021. And HG, as we can see here, is a measure of homophily from Pei et al. 2019, which is the proportion of edges that link nodes of the same type, of the same label. I guess this is a big table, and please go to the paper for full experimental details and hyperparameters and results. But our main takeaways were that stochastic discrete Ricci flow improves on the baseline in all cases, and Deagle does in all but one, which was more of a pathological case. And that SGRF tends to perform better in the more heterophilic settings and Deagle in the more homophilic settings. So they both give improvements, but potentially there's graphs and settings where one method may improve more than the other. And so I guess that's what we're saying. Both methods may give performance depending on your graph, and try both. Coming to the graph structure preservation. As we said with SGRF, the graph edit distance between the original and pre-processed version is upper bounded by twice the max number of iterations, because in each loop you're removing one and adding one. On the left here, we have the original Cornell graph, which is part of the WebKB dataset. In the center, we have the graph after a Deagle preprocessing, and right after the SGRF preprocessing. These are the graphs as performed best in our experiments. So these are specific hyperparameters chosen. The edges are colored according to Ricci curvature. So blue being negative and red being positive. And the nodes are actually colored according to the maximum Jacobian from the original 2-hop neighbors. So out of the kind of 2-hop neighborhood of a node's original node, how much information are we able to get from that node in our trained neural network? As we can see, both methods open up the bounds on the Jacobian, right? We can see from the Jacobian that there's a lot more variance. There's a lot more higher values taken outside of the two very central nodes. But as we discussed, the kind of more iterative and surgical process has preserved the graph structure or the distribution of node degree more. And so if we look at some statistics surrounding that, on the left, we can see a table of percentage of edges added and removed by each method as performed best in the experiments. And we can see kind of what we were discussing with Hans just now, in that Deagle, to achieve its best performance, often adds many more edges, not necessarily to match performance or improve performance, but to achieve its best performance, it will make the graph far denser on all data sets, whereas SGRF will keep kind of the graph edit distance maybe within 10-20% of the original graph. And on the right, we can see distributions of node degree in two of the graphs. So Wisconsin being one of the small WebKB datasets and AXA being one of the larger heterophilic datasets. And you can see that many nodes end up with this kind of larger peak towards the right, where they've become very dense, possibly because of the K term being fixed in the Deagle method. And so, so just to wrap up now, and then I guess we can return to the chat, which is popping off, and talk about some questions and discussions. Oversquashing induced by topology can be a problem for message passing neural networks. We propose a discrete notion of curvature called balanced Foreman, which makes sense on standard graphs. It's bounded above by alleviate, and that lets us borrow some of the theoretic results such that a positive Ricci curvature means a polynomially growing receptive field rather than the exponentially growing that we saw was a problem in oversquashing, and also that negatively curved edges are those responsible for bottlenecks, which gives us a clear target to try and tackle this problem. And then finally, the curvature-based rewiring methods, such as our initial proposal, SDRF, have a place in the literature and a place in your toolbox for trying to improve GNN learning on certain tasks, which improves on the baselines with these controls changes to the topology. So, thank you very much from all of us.
Oh, thank you for the fantastic paper and the fantastic explanations. Yeah, and then let's maybe keep going with the fantastic explanations with a question from Johnny.
Yes, I have a question. How many layers are you using in the GNN?
Good question. We let it float as a hyperparameter in the same way as the Deagle paper. It was largely selected to be between 1 and 3.
So how are you sure that your rewiring method is indeed like approaching the oversquashing?
Like, as opposed to underreaching?
No, like, I mean, if you don't have so many layers, I mean, I guess you are not going to have oversquashing. So how are you sure that your rewiring method is indeed tackling, like approaching oversquashing, and it is not like a fact that, I don't know, you are like looking at a higher order relationships or something like that?
So I'd say that in the beginning, we tried to distinguish between oversquashing and oversmoothing. And I think that large neural networks are often the cause of, say, oversmoothing, where you find that you kind of, each node has most or all of the graph in its computational graph. Whereas oversquashing is more to do with the bottlenecks. So if you know the diameter of your graph, or you know the structure of your graph such that you know your network isn't underreaching, and it's not like we forced a low layer choice, it was fixed by hyperparameter tuning. If you're not underreaching, then these performance degradations may well be down to oversquashing, and if they're improving by a method targeted to oversquashing, then I guess that's the improvement we're trying to show.
I think also to answer also a bit your question, remember that you are doing a pre-processing update on the topology. So for example, you may have, say, your optimal layer. I don't know whether you're still listening to me, just because you. I was seeing your face now. But what I was saying is, like, you can say your optimal hyperparameter depth, whatever, is 2, right? But perhaps you had nodes that were initially in the graph at distance 4, but after your curvature wiring, now they're distance 2, so they can be actually reached. So remember that we are not looking at the input graph. It's a good question, actually, in the sense, probably, yeah, we should investigate this more thoroughly, as in to what extent we are reaching the right nodes. But remember that in general, by addressing bottlenecks, you are decreasing the diameter by allowing more shortcuts. So this is partly addressed by that, and you don't need many layers as you would on the input graph.
Okay, thank you.
I think, yeah, Johannes, maybe, I don't know.
Yeah, hey,
yeah.
Thanks a lot for your great talk. Very interesting. I actually have a lot of questions, but I'll sort them by relevance and maybe threshold. The first question I wanted to ask is, in your definition of curvature, why did you stop at 4 cycles? Is there somehow is there a reason to exclude 5 cycles or other motifs to measure local connectivity? Is it purely computational, or is there a reason that these motifs are not relevant?
No, they are relevant. So so there are three answers I have. So one is the easiest one is the computational. You don't want to keep track of higher order structures indefinitely, otherwise it gets expensive. Also, the second answer is that Olivier curvature stops when you look into the Bastian formulation of Olivier curvature. It stops to essentially to 5 cycles. That's the most it can distinguish for each edge. Thirdly, you don't want your curvature notion to be a good curvature. It has to be intrinsically local. So you don't want it to be too sensitive, because a good thing about curvature that we've never mentioned, I guess, in this talk is that it is truly local, so it is robust to perturbations that are. So if you perturb the graph in some region, the curvature is not going to care outside of that region because it's a local map. If now you let this map depend on higher order structures, it will become more sensitive, which is not what you want. Otherwise, you end up with something like the spectrum of the Laplacian, where the minimum graph modification can affect it very much. So these are the answers I could give you. The most important being the computational one, though. Yeah, otherwise it gets very expensive. Mm-hmm.
Is Olivier curvature local?
Yeah, it is. Yeah.
Is it? Yeah.
Yeah. Cool. It is locally in the sense that it goes up to 5 cycles. This is the most it can distinguish for a base that a given Jij you're looking at.
Thanks a lot. I have more questions, but maybe I'll let Yuri go first.
Maybe we can cycle around. Yeah.
Thanks a lot.
I don't have any specific question. I just want to say that this is really good work and very interesting. And I personally tried to, after we submitted the over-squashing paper, we tried for many months to do something like yours and analyze and give some quantities and measures for over-squashing. And we eventually didn't find anything as solid as this, and we settled with just demonstrating over-squashing empirically and intuitively. So this is a really great work that does this measurement of over-squashing really well, and great work. And congratulations on your acceptance.
Thanks.
Thank you.
Okay, then maybe I'll go with one of my questions, but only before or only after I said that I think everybody totally agrees with Yuri's opinion here. Yeah. Then if we can maybe look at a few slides after, or no, I mean we're trying.
Which slide?
Yeah, no, let's just say we're trying to we want the original graph structure, right? Or this gives us a nice inductive bias that we want to use. But computationally, we have some problems if we use that as our computation graph. Yeah, then isn't the solution or the way forward for the future maybe to use graph transformers where we have none of these problems, but we can still have access to all of the graph information if we're using the right position encoding?
Okay, I can give you my answer, and then Jay can give his answer. He has better answers. So first, I think there's so although from a mathematical perspective, so the one answer I don't like, but it's actually probably the most important one, is that if you look at any possible pair of interactions, that is kind of throwing away all the goodness that comes with sparse matrices, and so
yeah.
The second answer is a question. It's like not for you, but for the world. So it's like there is these transformers papers that I think they probably want to get GNN people, out of their jobs. if at some point they realize that you don't need the graph structure anymore.
But I mean, they don't ignore the graph structure, right? They try to encode it in some way.
Yeah, of course. But you know, personally, you know, what I like about this method is that it's not empirically you get some good results and then you say, well, it's probably because I have done some encoding and my model has managed to do some encoding of higher order structure as well, or whatever. I think it's more about shedding as far, you know, as much light as possible on the actual topological, you know, aspects of the graph that can be a reason for some problem to happen and for modifying that. And I think in terms of investigation, for example, of expressive power as well, like most of papers, they do this WL test and, you know, whatever. Yeah, okay. But like, for example, these type of problems are how information propagates. It seems much more relevant in the message passing neural network. And, you know, this curvature is intimately related to the graph structure. And now there's a whole business of, as I said, it's an open question to what extent you want to carry over the topology and how you want to use that information. That surely helps us somehow, but how you want to how you want to use that. I think it's a much more controlled way to do it rather than using some positional encoding and hoping that you're going to capture long-range dependencies by doing so beyond being more expensive computationally. I think.
Okay, cool. It's a fair opinion, right? All right. Then, Johannes, I guess we can go on with some of your questions.
Thanks. I also wanted to ask about the Jaeger constant. I find the comparison interesting. I mean, the Jaeger constant is defined on the basis of node subsets, and your Ricci curvature is defined on edgewise. So obviously, you rightfully mentioned the Jaeger constant is too expensive to calculate to really be used. But have you looked further into this comparison? I mean, do you see other advantages that your curvature has over the Jaeger constant beyond that it's computationally cheaper?
The Jaeger constant is also global, right? So the actual Jaeger constant is just a number that is associated with your graph. And so it's a very, you know, it's just a scalar. And also, it's like if you give me this, essentially, really, it's like controlling the spectral gap. So of course, yeah, okay, it's interesting, but like it doesn't give you much information because it doesn't see the edge. It's not distributed over the edges. Also, it is a measure of how easily you can disconnect the graph into two communities, but not in more than two, for example. So it's a very kind of superficial type of information. It's relevant because it has very nice connection to the spectrum of the graph. So it is like a prototypical example how the topology of the graph can be intertwined with the spectrum of the Laplacian via these isoperimetric inequalities, but it is at the end of the day a very rough object. What I want to mention actually, what is I think still in the appendix of the paper, some reviewers didn't like it in a previous version, so we had to remove it. But and there was to leave space for more. But what we actually investigated is that there are actually there are theorems in the appendix that show connections between a curvature and the betweenness centrality. So the betweenness centrality now instead is node-wise defined, or it can be even edge-wise defined, and it's a more refined version of Jaeger constant. And not surprisingly, this is again, if you like, another face of the coin of the curvature. So, and this was initially proposed as some sort of more topological measure of bottlenecks. So, because of course, if you have bridges or whatever, they're going to have high betweenness centrality because most of minimal paths will go through these bridges. So this is yet another classical graph notion that can be linked to curvature, to discrete curvature.
I think a nice words, or the nice words in which you put it in the paper already is curvature-based rewiring is surgical, and like GIGA would be like global or not surgical.
Yeah.
And I also wanted to ask, in your dumbbell graph, you speak of this single edge connecting the two communities as a bottleneck. But if now somehow we're in a setting where the label of nodes correlates to the structure of the graph, meaning that we do want to label this graph into two communities, the two communities being defined by the two ends of the dumbbell, then this bottleneck to some degree is beneficial, isn't it? Because for
That's a very good point. Yeah, there's actually a paper published in Nature in 2018, Ni et al. I can't remember the name, but they ran, I guess, a more traditional Ricci flow using alleviate curvature on the metric of the graph. And what that would have done in this case would have made that central edge increasingly expensive to cross, and then they would perform surgery and cut it. And so their method was for clustering. It was based on exactly that assumption that you said. Nodes that are more connected are more likely to be related, like an assumption of homophily. And so they used Ricci flow there as a clustering method. And yes, if you could take other information into account, then you could improve the method. But that's one thing I guess we'll have to stay tuned for.
Yeah, but I think you're right. Like ideally, when this graph, so ideally, when what homophily means really is that there is a high agreement between the graph topology and the label distribution, at least for node classification. So when such a high agreement is available, it means that community that are topologically defined are actually community that also are consistent with the label assignment. And this is like, this you can use a heat equation really, or GCN to do classification on such a dumbbell. So these of course are easy cases. Like this is why I think we should have probably stressed this out more. But I think what you should have in mind, at least when you, in terms of node classification, it's a problem where it's no longer true that your neighbors would on average share the same label as yours. It's more about you should reach for perhaps either further distant nodes, or to get meaningful information, you have to cross bridges. It's not enough to just access your neighborhood. If it was, then you can use your heat equation or GCN, which and that would be more than enough, right?
Exactly. So, this one of the kernels that they use in the Deagle paper is the heat kernel, right? Yeah.
That's right. Exactly. Yes.
So this is, I guess, one reason why your method shines in the context of heterophily, right?
Yes.
Yes.
Okay.
That's right.
Thanks for your answers.
Thank you. I don't know if we've missed any in chat. There's been great discussion there. But if there's any other questions, please shout out.
So the chat recently was a discussion between a few different people, so you don't need to answer questions there, I think. I just, one of the propositions that I've done is renaming oversquashing and oversmoothing as oversquashing would be stuck in traffic and oversmoothing lost in traffic. And this would help, I think, better guide the community to what is the real underlying problem. It's traffic. And the solution you're proposing here, you build more roads, you reduce traffic. Now, what are the other kind of solutions that we can look into there? And one of the great things about your paper is how to measure traffic. Like, how do you measure which edges are the bottlenecks that means that cars get stuck there, or that information gets stuck there. And it's very important in my opinion, because like when you know how to measure the problem, you can look into how to solve the problem. And this is I think what you've done in this paper you've built the first steps into solving the problem. But the most important part is like the foundation that you've built about measuring the problem. Now everyone can go and tackle the same problem more efficiently than before. And I think it's a great paper, and it definitely deserves to be an oral presentation at iClear. And thank you a lot for presenting it.
Thank you so much. It's been a pleasure.
Great explanations, and I think with this new notion of curvature on graphs, we can expect to see many new applications and many new ideas to follow up on this work. And if you want to join the reading group yourself, all the information is in the description. You can join our Slack or our email mailing lists to get updates.